Hello, I'm Brianna Dickinson, and with my partner Robert Trombley, we are going to demonstrate our project for electronics at Oregon Institute of Technology. We built a regulated power supply. So the project specifications were that we could plug this into a standard wall outlet at 120 volts and 60 hertz AC, and it would be externally adjustable to give 5 to 10 volts output. It could also produce a current of up to half an amp. So the constraints were that this regulator could be either a series or a shunt regulator. It had to have negative feedback, current boosting, and overdrive protection. We weren't allowed to use monolithic integrated circuit regulators. We had to build our own. So our circuit looks like this. We did not model the transformer that we used to step down the voltage from 120 volts. We chose a 15 volt step down transformer. So our schematic here just shows the input coming out from the transformer, not from the wall. So first, after the transformer, it hits the full bridge rectifier, and then it hits the capacitor to smooth out the ripple from the rectified signal. This is the bleeder resistor, so that when the load's not connected, the capacitor can discharge. Then it goes into this section, which has the Zener diode and the Zener biasing resistor. They feed into the non-inverting input of the op-amp. So the Zener diode is the basic voltage regulation, but the op-amp and the pass transistor right here offer improved voltage regulation. So if the output voltage is trying to increase, that means that more voltage is fed back through the potentiometer and into the inverting input, which is the negative feedback into the op-amp. And this means that the output of the op-amp is reduced, and the base voltage of the pass transistor is also reduced, which means that the overall circuit output, the output voltage, is reduced. So as it's trying to increase, this negative feedback in conjunction with the pass transistor reduces that increase. So it works the other way, where if the output voltage is trying to decrease, then the op-amp voltage, it increases the voltage to the base of the transistor, which means that that transistor helps offset the output voltage decrease, which the Zener diode on its own is unable to do. So this setup right here, where the op-amp goes into the base of this transistor, it is actually boosting the current coming out of the op-amp, because by itself the op-amp doesn't produce much current, but with it tied to this transistor, it boosts it, so when it goes to the output, there's a higher current out of this power supply. So the last part is overload protection, which is this part, which is current limiting. So both this transistor and this resistor are current sensing, so when the current of the circuit is too high, this transistor will activate and lower the current of the overall circuit. So now, to demonstrate the adjustable voltage, we will run this circuit, and I'm going to zoom in a little bit so you can still see the circuit down here. So here's the potentiometer. Right now we have a relatively low resistance load, 20 ohms, and a kind of low potentiometer voltage. So here we can or sorry, this is resistance. Here we can see that the output voltage is about at 5 volts, which is the lower end of what we need. And so if we change the potentiometer to, say, 3000, and we run it again, while there is some ripple in it, it's kind of small, but it shows that it's not quite getting to 10 volts, but it's pretty close. It's 9.9, which is what we're looking for. So to show current limiting, if we go above 3K, say 5K, it should still have a limit of 10 volts, which is what it's showing. So it does have current limiting on this circuit, which is the last of, well, that and the adjustable voltage output, which is what the potentiometer does. So now my partner is going to do a lab bench tutorial where he goes through our actual circuit and demonstrate that it works in an experimental setting.
Okay, welcome to our voltage regulated adjustable power supply. I'm just going to walk you through the circuit, point out all the pieces, parts. We've got on the far left power coming in out of the wall, approximately 120 volts RMS, through the transformer, coming out the far side, approximately 18. Coming down into either side of our bridge rectifier unit, coming out of the bridge rectifier and into this node here with the large capacitor, bleeder resistor, and connecting all the way over to the Zener biasing node right here. At the Zener biasing resistor, we pass through to the Zener diode itself, thus setting our voltage for the input at the non-inverting input of the op-amp. And the op-amp is powered on the positive end back to the same spot as the biasing resistor, and at the negative down to ground. Coming out of the op-amp, across this resistor, into the base of the pass transistor, as well as at the same node to the collector of the current sensing transistor. Notice our pass transistor equipped with a heatsink and a separately powered small fan, because sucking half an amp through a tiny piece of plastic gets kind of hot. The pass transistor is connected back through the same node that's powering the op-amp, as well as all the way back to basically the top of the rectifier. All one node there. And it's passing the current through out the emitter on to the base of the current sensing transistor, as well as the current sensing resistor as part of the protection circuit. From there, we pass on to the node connected to the potentiometer, which feeds not only as a voltage divider between the load as well as the negative feedback loop back into the inverting input of the op-amp. And at that point, we can show that with our pot, when we fire up the power, see here, we're at a voltage of approximately 5 across our load, and by turning our pot, we can adjust that all the way up to 10, almost 10. As you can see there, the current limiting kicks in, and as I continue to turn, it just stops at 9.7, 9.8 volts, thus protecting the load from current surge. Thank you very much. I hope you enjoyed your tour.